one of the basic problems in algebra is finding the roots of the equation. In a sense, this is really what algebra started out being. The book itself, the Compendium on Completion and Reduction, Al-Yabar et Mukabala, et Al-Mukabala, was written to create a method that was far more mechanical than the geometric solutions of the time. But finding the roots of a particular polynomial is hard. Something like this. That's fairly difficult. Much less higher powers. There are formulas for these. There's a formula for solving any cubic equation. My buddy Tartaglia and Cardano came up with it. It's disgusting. Now, what really bothers me about this is that there's a square root inside a cube root. Twice. That's nasty. And if I want to go to a degree 4 equation, I'll get 4 different solutions. And when I tried to print out this formula to fit it on a single sheet of paper, I can't read it. That's ridiculous. Root 1, root 2, root 3, forget it. This is garbage. And it makes no sense to try and bust our butts to try and solve directly like this when I can do things like my linear approximation. I was able to find an approximation for the square root of a weird number, right? What did we use last time on Friday? Square root of 1700, because it was cube root of 1700, right? But that was really, if I'm finding the cube root of 1700, that's the same as saying I want to know where that equation is equal to 0. So finding the root of a particular value is the same as finding an x-intercept on a graph. So what I'd like is a better method. So let's take our linear approximation and let's mess with it a bit. Let me think about this. I have some equation, and my goal is to figure out where this is 0. Now let's suppose I have a wild guess. I have no idea how right or wrong that guess is. But what I do know is that I can create a linear approximation. At that point, I have a slope, f prime of x1, and I have a point, so I get an equation. Y minus the y value here equals m times x minus the x value there. That's my linear approximation's line equation. It's not the way we used the linear approximation LF, which would have moved that to the other side. But let's draw a picture. We drew the picture on Friday. I'm going to cheat and steal the picture right from the book. Here's my picture. There's my point x1, f of x1. There's my tangent line. There's my linear approximation. See how good it is right there? But notice, that line has an x-intercept. And the x-intercept is closer to where the graph has an x-intercept than x1 is. How can I find this point? I want to know how to get that x value. But I already have the equation for that whole line, don't I? That is the equation here. But you're right, I want to know where the y is equal to 0 on that line. Well, if I take this and I set y equal to 0, I can solve for x. So if this is 0, I have minus f of x1 equals f prime of x1 times x minus x1. My goal is to get this all alone, so I'm going to divide first. Now I have those parentheses. Parentheses are effectively irrelevant at that point. I just need to move the x1 over. So I add x1. And that's my value for x2. So I found a way to move closer to the root. By doing this, I've moved closer. So if my goal is to actually keep getting closer, what should I do? I should do this whole same thing again. From this x2, I can go up and make a tangent line. And I'll draw that tangent line on this picture we just had. I'll go up here, and I'll draw a tangent line here. But notice that that tangent line will come further to the left. It'll get closer to R still. As a matter of fact, if I keep doing this process over and over and over, my chain of x-intercepts gets closer and closer and closer to that root every time, almost. But I'm going to end up with this same formula being used over and over. So I'm going to write it in general, and I'm going to create a sequence. If this sequence has a limit, that's my root. Now, this actual idea was proposed by Newton. It was refined by a guy by the name of Raphson. So this is known as the Newton-Raphson method. I should do an example. But before I do that example, answer me one question. Where is some place that you know this sequence will have a problem just based off of this formula? I'm ever dividing by zero, I'm screwed. So if there are any places, if I just happen to hit a place where the derivative is zero, I'm in trouble. Or if I pick a place where the derivative is undefined. So I need to make sure that for my x1, and ideally for the rest of the sequence, that these functions and their derivatives exist. Since we are picking these numbers basically out of thin air, I am going to tell you right now, it's really, 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 really rare for us to pick a value that is exactly where the derivatives are. It's not impossible, but it's going to be a really small chance of doing it randomly. There is no requirement that my function f of x be of any particular type. It can be a polynomial, it can be rational, it can be trigonometric, exponential, it doesn't matter. As long as I know how to take the derivative of the function I'm working with. So here is an example. Now, before I do anything, I'm going to draw a picture. Just to see if I'm even anywhere close to a root when I start at 2. So I'm going to graph this function. Here it is on the standard window. Okay, there's an x-intercept. And that x-intercept looks to be between 1 and 2. So I think starting at 2 would be a bad idea. Yep. Somewhere between 1 and 2. We go from positive values to negative values. So I need this formula in front of me. Write it off to the side. Make sure you can see it. Let's keep doing this. That means I need f prime. Take the derivative. Because this is x to the minus 1. When I take its derivative, I get negative x to the negative 2, but a negative 2 power means it goes on the bottom. Now, here's where this starts to get ugly. Because what I need to do to find x2 is to take x1 and subtract What happens when I put 2 in here? And what happens when I put 2 in here? Okay, so up here, 1 minus 4 plus 1. One and 1 is 2. Subtract the 4, you get -2. Down here, I have -1/2 minus a 4. That's -4.5. I'm sorry, what was that sign?
Is it? Oh, how's it top negative two?
Because that's positive. That's positive.
Oh, okay.
The subtraction's outside. Notice, though, that this negative and this negative, they're going to cancel each other out. So this is going to be 2 minus, I'm going to multiply top and bottom by 2, 4/9. So this is a disgusting looking number, 1.5555. The fives keep repeating, right? Now, I'm the first person to tell you that the problem comes from the next step. I got to do it again, which means I got to plug this number in, both to the function and to its derivative, over and over. This is not pleasant to do by hand. So I'm not going to. To get x3, I need to take x2, then f of x2 over f prime of x2, right? Now, two minus 4/9. That's our x value, 1.555555. If I just hit the trace button and I enter that x value, I get the y value right there. That's this top number. So I don't actually have to do that work by hand because I have this piece of technology in front of me. But I can do the same thing with the derivative. Hit second and trace. What happens? That's this calculate menu above the trace button. When I hit second and trace, one of the options there, option 6, is a derivative. It will compute the derivative, and I need to give it the value. If I type in 1.555555, however many fives you want to put, I wrote at least 4, so we should do at least 4. There's my derivative. That's the bottom number. You'll notice that this shows at least 6 decimal places. I would keep at least 6 decimal places unless you're asked for a certain number of decimal places by the question. Okay, wait a minute. I need to do this calculation. I go out here to a blank screen. Negative 0.1340388 divided by negative 3.937642, and I'm closer. That's x3. Let me write that down. Now, I need to copy that number so that I can go back and put it in the graph. I don't want to write this number down over and over and over again. So I'm going to store this number in my calculator. Way down here on the left is an STO with an arrow. It says store. If I hit that, it's going to take the number I just gave, give me a little arrow. It's going to ask, where do you want to put this? Somebody pick a letter other than X.
T.
So I have a T right here. See it in green? To the right above the 4. The green button says alpha. That's the alphabet. There's T. That number is now stored in T. You can put it wherever you want. I don't care what letter. I just don't want to use X because the calculator is using X on the graph. I'm going to take that number, go back to my graph, and say, trace. Now I want to put in that number to get X4. And that number is going to go up here, whatever my Y value is when I put in that number. How do I put in that number here? If I hit the trace button, I can simply type alpha T, and I'll use whatever number I stored in T. And there's the number we stored in T. And there's our Y value, negative 0.000529, because that E4 means I have to move the decimal place over 4 spots. E negative 4. That's why I moved it to the left. Same thing with the derivative. Second, trace gives me the option 6. Where do I want that? I want that at T. Negative 3.906958. Please give me the value for X4.
One point five three, 1.7.
1.52137. Now I'm actually going to type that in here. 1.5, sorry, it's T. T minus,
There's more decimal.
oh, hang on. 0.000529 divided by 3.906958. I'm good with writing down only a couple of them, but I'm going to store them back in T again. So that I can do this again and again and again until I get through however many decimal places is the right number for the application I'm doing. Now, if I only wanted 3 decimal places, I could stop, because X3 and X4 are the same to 3 decimal places. If I wanted 4 decimal places, I'd need to keep going, wouldn't I? So now it becomes a question of precision. How precise do you want to get? What's your epsilon? Back in that same situation. If I use the calculator, I can get the calculator to do this to 9 decimals, because that's how many the calculator will keep in its memory. Questions? At the bottom of our web links section is a video by Grant Sanderson, who runs a channel called 3 Blue 1 Brown. And he talks about this exact idea. And it turns out that there are cases where we won't get a nice answer. This sequence converges almost all the time. Underline that word, almost, which is infuriating, because sometimes it eats us up. But it really only messes us up if we happen to pick the exact wrong starting point. There's no requirement that I use a polynomial. There's no requirement that I use any particular kind of function, as long as what I'm dealing with is differentiable. I can use this to solve equations for which I have no formula. So here is the equation that for some reason, as I was working through my problem, this is what I came up with. I want to solve e to the x equals 4 minus x squared. Now I know the graph of e to the x. What's the graph of 4 minus x squared look like? That's e to the x. What's the 4 minus x squared part? See? It's a downward opening parabola. The x squared makes the parabola, the negative in front makes it open downward. If I graph these as separate equations, then I can see here's e to the x, there's the parabola, and there is clearly a place where those two cross on the left. So I want to know, where do they cross? If I zoom in, it looks like it's over there. Wait a minute. That's -1, so that's -2-ish, right? If I actually put in put in -2, I can see that they're ever so slightly different. One of them is at 0. The other one isn't. The parabola is exactly 0 at -2, but the exponential isn't. So they've got to move a little further over. They should cross somewhere over there, a little bit to the left of -2. Well, if I know they're going to cross a little bit to the left of -2, that should be where I start. The closer I get to a good starting point, the better I am. But Newton's method only works if I'm dealing with an equation that is equal to 0. So the first thing I'm going to do is put everything on one side. So now trying to find out where these are equal is the same as trying to find out where this function is 0. Now I want you to keep as many decimals as your calculator will let you. And I want you to get until you get 2 answers in a row that are the same for 6 decimal places. There's my formula over there on the right. I need to make sure I have that formula in front of me so that I can do this process. I need f prime. So if I'm going to do this, I need my derivative. What's the derivative of this function? I'm looking for where the y value is 0, but I just need to know the derivative. The derivative of the 4 is 0, but what about these two pieces? Derivative of e to the x is, and the derivative of x squared, there you go. So that's what I'm going to plug in -2. Now that means over here in my calculator, I need to change that equation to be the one I want to use. And I need to make sure my window includes -2 so I can start there. Trace -2. So there's my y value. 0.135335528. Over. Now I need my derivative. Second, calculate 6. I need to give it the x value. The x value is -2 exactly. My derivative is -3.864665. Notice that's a negative slope. We are going down as we go from left to right. If we drew a tangent line here, so we're going to move to the right because I'm going to end up adding something to -2. -2 plus 0.135335528 divided by 3.864665. 1.964981. Since I only need 6 decimal places, that's all I'm going to write for now. You could write all of them. Matter of fact, let's go ahead and do that for the moment. But let's remember we only need to keep track through there. Now I'm going to store this as a letter so I can use it later. I'm going to store this as A, so I have access to it in A. Now I go back to the graph and I plug in A. And I'm going to add on top 0.00131028. Over. Now I calculate my derivative. Same setup. Second, calculate option number 6. Plug in A. And I get 3.789804. 804. Notice minus a minus means I'm going to add. Take A and add 0.00131028 divided by 3.789804. There's my new number. -1.964635. 3456. Those are not the same to 6 decimal places. I need to keep going. So I'm going to store this as my new value for A, and I'm going to do it again. So I start by putting in the value, trace, plug in A. Oh, look at that. That's a tiny little number, e to the -7. So that's 0.00000012385 over. Second, calculate option number 6, plug in A. 3789064. 3789064. Calculate X4 for me. What do you get when you calculate this value? Please notice the resulting number. -1.964635597 is the same to 6 decimal places. Only took me 4 steps to get close enough. Questions? I would point out to you that when we are trying to find roots, we're really looking at a function of the form x to some power minus a. You want to find the square root of a number, you use x squared. You want to find the cube root of a number, you use x cubed. Find the 17th number, use x to the 17th, right? But if I use x squared, then its derivative is just 2x, right? If I go back to our formula, xn plus 1 is xn minus xn squared minus a over 2xn. Well, wait a minute. Let's break this function up. Minus xn squared over 2xn plus a over 2xn. What happens here? So I'll get one xn. Instead of a square on top, I'll only have one. So, and that'll make this xn minus xn over 2. This is thing minus half of thing. If you take a thing and subtract half of it, you're left with half of it, right? So this is 1/2 xn plus 1/2 a over xn. Pull out the 1/2. This formula for a square root is 3,000 years old, if not older. This particular formula was known and written down by Babylonian mathematicians. That's, seriously, 3,000 or more years old. It was translated into Egyptian, and the Egyptians used this. But that meant in 2 or 3 steps, they could find a square root. Without ever using a linear approximation directly, they knew how to get square roots with straight lines. Calculus is less than 400 years old. The ideas of calculus are thousands of years old. Questions? I'm going to throw a monkey wrench at you. This is a cubic equation. How many roots should it have? It should have 3. Problem. Only one of those roots is a real number. The other 2 are complex numbers. The real one is 1, but the other 2 are complex roots. Now, complex numbers don't live on a number line anymore because they've got a regular part and an I part. They live on a plane, with the I part going up and down and the real part going left to right. I don't know how many of you did complex numbers in your algebra or pre-calculus class. I want to mention this to you. Newton's formula still works in complex numbers. Here's where the weird part sets in. I'm going to take this idea and I'm going to put it on a computer program, which, by the way, you can even do on your calculator. You don't have to have a really powerful programming thing to do this program. It exists on the calculator already. I believe this is already on our Canvas page for you to have, but it'll be a copy of this in the notes. So I started coding this. And what I decided I was going to do was I was going to take every possible starting point I could take. And I was going to use them all. And if they went to 1, I was going to color them red. And if they went to this complex one, I was going to color them green. And if they went to this complex one, I was going to color them blue. Well, here's the fun part about that picture. Clearly, everything over there is red. It's going to 1. Everything up in that corner is going to green. That's going to the positive net root 3 over 2 I part. Everything down here in this corner is going to the blue. But look at what's happening in the boundary regions. Oh, positive 1 is right about here. 1/2 is right about here. That dot, where all those bits come together, that is the starting point, x equals negative 1/2. If you pick x equals negative 1/2, you will bounce all over doing Newton's method. The edge of these regions are so twisted and interconnected that at any point where any 2 colors touch, the third color also touches them. And that means if you pick exactly x equals negative 1/2, Newton's method doesn't have a derivative equal to 0, but it fails to converge. The limit of our sequence bounces all over that edge. This, by the way, is one of the original definitions of what it means for a system to be chaotic. So when math geeks and science and computer geeks talk about chaos theory, they're talking about how crazy this boundary region is. They're talking about how if you move ever so slightly, just a little bit to one side or the other, you'll get a completely different answer. If you are at exactly -1/2 and you shove yourself a little bit to the left or the right, you're going to go to the red region. If you shove yourself a little bit up, you're going to go to the green region. A little bit down, you're going to go to the blue region. It's going to depend on where you are as to what you can see and how tightly you control that little epsilon you've picked. These, by the way, are called Newton's basins of attraction, and they show the methods by which our convergence in the sequence of roots occurs. Ladies and gentlemen, this finishes the material for chapter 3, and this particular section out of chapter 4 got done in this order because it is a particularly good application of linear approximation. This is also all of the material that is on the next exam. Normally, that would mean that Wednesday is question and answer day, but what is Wednesday? Therefore, there is no class on Wednesday, and that means Thursday is question and answer day. Friday, the homework is due. Our exam is a week from today. The review sheet is already on our Canvas page. Please bring your questions on Thursday. I will see you then.